Welcome to the DIF, the online festival of ideas that asks the question, what if we could redesign everything? A fundamental requirement for a circular economy to work is to use positive materials and chemistry only. Chemistry binds together materials and possibly holds the key to make safe material flows work. My name is Emma Fromberg and I will be your host for today. Don't forget that this is an interactive session, so make sure that you send all your questions to the discussion box on the right-hand side of your screen or use Twitter #ThinkDiff. Today with me in the studio we have Patrick Maestro, Scientific Director of Solvay, a company which deals with chemicals. Welcome, Patrick. Thank you for coming to the studio.
Thank you, it's a pleasure.
So you are a material scientist, and this is an online festival which basically bridges technology and the economy. So what is the role of chemistry in all of this?
The role of chemistry is everywhere. Chemistry is everywhere in our daily life. You need chemistry to get electronics, you need chemistry in automotive, you need chemistry in aeronautics, in home and personal care, everywhere. And when we are dealing with circular economy, I'm convinced that chemistry is the enabler, as this is the science and the technology that will allow you to make the global recycling and to make the global circle of circular economy. Because through chemistry you can recycle metals, you can depolymerize polymers, you can reintroduce them in the global chain using some other chemical reactions. And so chemistry is really everywhere in the circle.
So you work for the company Solvay. You have been very intrigued by the topic of a circular economy already early on. How have you been applying this so far within your organization?
First, a few words about Solvay. Solvay is a 155 years old company. It has been created on the model of innovation and sustainability. And since this creation, Solvay has always been involved in making a sustainable chemistry. For that, we are more and more taking into account the circular economy, the sustainable development. We want to make a chemistry which is responsible, and circular economy is really part of the global commitment of Solvay in sustainable development. And we have, since several years now, been involved in having a sustainable requirements in all our projects, in all our processes. And we have some examples that we can disclose already, and we will have more in the future.
Okay, so first example that we're going to put up.
The first example is what's so-called My H2O2 is a way to put on, as you see on the slide. We are a big worldwide supplier of hydrogen peroxide that goes in several industries, and particularly in the paper pulp industry. Mm-hmm. And what we have been able to develop in the recent years is to put the so-called satellite peroxide production on the site of the pulp makers. So what you see here is the plant where you see with the arrow the place where we do H2O2 that will go into the global circle of the plant by recycling the system. Then we go to the next slide, and it's done it's shown in a rather simple way, but you can see exactly what is happening. Well, we sell H2O2 to the pulp manufacturers, and from the preparation of the pulp, you get oxygen and hydrogen. And through our chemical process, we recycle the H2O2 that goes back in the circle of the pulp making. And this is a new circular global business model that avoids logistics, of course, that is one of the main impact, and that puts all the chemicals back in the loop on the continuous process by using, of course, our technology to recycle H2O2.
So there's no waste leaving the factory?
No, in fact, the waste effluents are treated globally, but the waste is recycled all the circular.
So also in the treatment, there's nothing that leaks out of that.
Yeah, exactly.
And how is it currently done in other industries that do similar types of things? So this is to create the pulp that is in the fiber of paper, right?
Yes, to extract the pulp from the wood and to
Okay.
make paper.
And they're usually at two different places, so you have the logistics in between.
If not, no. If they need H2O2 as a bleaching agent, and so either you get it from outside with transportation, or you recycle the H2O2 inside, which is what we're doing with this kind of small plants, really located in our customers' places.
And how
And
many
the
of
connection with the customer is really key in this for these kind of endeavors.
Because how many of these plants are...
Today you have seen one. Our plans are to make more, and this is on the way by the business unit, as a matter of fact.
Okay, so you are responsible for the chemical reaction which happens in the plant, and you work together with other manufacturers.
The connection in this kind of project, the connection with the customer is really key, because we define together what are the needs and how we can enter in the loop globally.
Okay.
And it applies to every kind of project that we may have in circular economy. We have to work with the customer and with the end user, of course, to develop these kind of projects.
And why don't you do this all by yourself? Why do you work with another partner company?
We are not pulp makers. So we work in chemistry. We are upstream in the value chain, and we need to work with our customers to develop with them the processes.
And in the next example, we're going to look at a biodegradable yarn.
Yes.
Do you want to give a short introduction?
Oh, it's just, I think the video it will be self-explanatory, but it's really the way also another way to introduce our products in circular economy is to make them biodegradable, and then they can be reusable, which is one of the key points in terms of waste management.
Okay, so shall we have a look at the video and then discuss the difference between biological materials and technological materials? Okay, bring it on.
The word sustainable in the dictionary means conserving an ecological balance. Taking this into consideration, Roger, a member of Solvay Group and a pioneer in the development of the textile industry, manages its innovation to create sustainable solutions for the planet. Our researchers from all over the world are working to create products with the ability to provide a better quality of life for people. Focused on preserving the environment, Roger created the Omniso Eco, the first biodegradable polyamide yarn in the world. The improved Omniso Eco formula offers the ability for biodegradable clothing while still offering all the polyamide fiber benefits, such as soft touch, comfort, moisture absorption, easy care, and easy washing. After enough wear and tear, our clothes either don't fit or are worn out, and we tend to get rid of them. That's when Omniso Eco starts working. This yarn allows the clothes to quickly decompose after their disposal in the landfill. Millions of clothing items are disposed every year, generating a critical environmental damage. With a proper disposal process, garments made with this yarn are easily degraded, helping to reduce the environmental impact. Ultimately, this enhances landfill's productivity, waste biodegradation rate, and indirectly promotes the conservation of green areas. Furthermore, the whole manufacturing process of Omniso Eco is sustainable. Omniso Eco is not only a biodegradable yarn, it represents a commitment to the future generations by promoting eco-friendly clothing. And this is how we show our commitment towards a sustainable environment inside and outside Roger and the Solvay Group.
So this is one of your initiatives of Solvay?
Right.
And we saw a biodegradable initiative.
Yeah.
So how is that different from... Because if I think about chemical companies, I think about typically like maybe technological materials.
Right.
How is this different from what you did with H2O2?
It's another story, I would say. In this case, we have been doing, it's still chemistry, but what we have been doing is making a transformation of the polyamide, which is still the polyamide, classical polyamide, by putting through the chemistry something, well, some moiety that makes it biodegradable. And so in the end, we are able to favor the global circular economy, because this biodegradable polyamide will be reused to make new polyamide once it has been gone to the biodegradable end of the step. So finally, what we are doing here is that we are making something which is more easy to recover and to reintroduce in the global chain.
So
and this is through chemistry that we have been able to make this polyamide and to make it biodegradable.
So you say that chemistry is the enabler for a circular economy, but so I'm a designer.
Yeah.
You know, there are multiple players in this field.
Yeah.
What are the other enablers for a circular economy beyond chemistry?
Well, I would say technology at large, because sometimes chemistry cannot make everything, or you need to prepare to make the chemistry. So, for example, to grind, to use more the mechanical technologies, but chemistry will be complementary to it. But I would say that in terms of circular economy, one of the key enablers is the behavior of the people. I don't know whether it answers the question, but as long as we as citizens will consider more the selective sorting of the wastes, we will use less, in fact, less material, we'll use less packaging. So it's also part of the global behavior of the citizenship that we will enable more circular economy.
Is it behavior of people, or is it the business models and the services that we offer?
This is both. I think, again, the behavior of people is key. Then when you are entering circular economy, you will always have to take into account economical points. And it's true that sometimes the economics at one day can be negative towards the global circular economy scheme. But we have to think long term. We are thinking always long term within Solvay, and something which is untrue today may become true tomorrow, because the pressure for circular economy will be, given the state of the planet, will be enough so that we can afford to pay a bit more for something which has been involved in the circular economy. But also, again, the economies can evolve from one year to the other, depending on the global state of the world. So it's really something that we have to have in our beliefs to really make it happen, and that will be a way of integrating both the economics and the behavior of the people and the technology that will bring the solutions.
That it all comes together.
I'm sure.
So we already got a few questions from the online audience.
Yeah.
So from Jean Bellinger, we got the question, is the biodegradable yarn compostable? Is it?
I'm not sure we can go into compostable like you will think about compostable or vegetables. So
do I put it in the green bin?
Yeah. No, because it's still a polymer in the end. So
what do you do with it after use?
You recycle.
Okay, so you put it in the recycling bin.
It's really more to recycle. Yeah.
And can you use it to help regenerate soil?
No, I don't think it's the same thing.
All right, so don't forget to ask all your questions through the discussion box on the right-hand side of your screen, or use #ThinkDiff on Twitter. To make chemistry come to life a bit more, we created a random product selector, which will select some random products for us to discuss. And then the question to you is very simple. How can chemistry help to make this product fit for a circular economy? Are you ready?
Ready?
Yeah?
Yeah.
Okay, so we're going to spin the wheel now for the first product. A smartphone.
Smartphone.
Okay, so first question that I have on the smartphone, because I did a bit of research. Is it true that there are 62 different metals in each smartphone? Do you know?
There may be 61 or 63, but I'm sure there is a lot of metals in a smartphone because you have a lot of precious metals. They go mainly for the electronic properties. You have a lot of precious metals. You have gold, platinum, palladium. You have rare earths. You have aluminum. You have
What are rare earths?
copper. Rare earths are so-called also lanthanides. There are some specific elements that are quite unknown by the people, but which are very active in electronics. They are also active in catalysis. They are also active in magnetism. And they go a lot in these kind of systems because they have very specific optoelectronic properties like conductivity, emissivity, and Solvay is making these kind of rare earths. That's why I'm speaking about that. So they go a lot into the smartphone. So yes, I'm sure that there is around 60 metals in a smartphone. But there is also a lot of different polymers. And the smartphone is a very complex system that couldn't exist without chemistry, because again, chemistry brings the polymers, bring the precious metals, bring the electronics, bring the glass, the modification of the glass surface, and so on. Then, when we want to recycle a smartphone, again, chemistry can be the enabler, because in terms of precious metals, you can recover the metals, and chemistry will be able to separate the metals from each other by technologies that have been applied, for example, to the separation of rare earths, but that can apply to the separation and recovery of precious metals or any kind of other metal with a purity which is very high. We can go up to 99.99% of purity through the chemical methods of hydrometallurgy, through solvents, through dispersants, through extractants. And so chemistry will be very key in the recovery of metals. But again, I mentioned polymers because we supply a lot of polymers. The chemistry is really key in that. And the chemistry will be key in the recycling of the polymers from the smartphones.
So how does it work? Because I did see an example once of that you had like this motherboard or that printed circuit board.
Yeah.
You put that in like
Yes.
some sort of a liquid and then
Right.
things start to bubble up and start to
Exactly.
split.
Yes, at some time you have to dismantle the system. Then, of course, you have to separate the polymers or the resins from the metals. So again, back to solvents, to acids, or some chemical treatments. Then you can separate the part of which is the resin that goes back to we can go back to the basic molecules, and then you have the mixture of the metals, and then you have several possibilities that we use in mining, for example, that you can use in this kind of schemes to reseparate and to purify the metals one from each other.
So don't you have like, you need to basically add chemicals to recycle them chemically. Don't you have a lot of waste?
But you can recycle the chemicals from the waste also. So that can be also a very virtuous circle, because in this case, you will be able to recycle the chemicals and to reuse them. So it's again a complete circle where the chemicals can be used to separate the resins from the metals, that can be used to purify the metals, but then can be recycled by again other chemical treatments to re-put them in the global chain.
But don't you think that it might be more effective to, for example, with a phone, they often reach their end of life because the battery, dies or is not performing well enough. Do you think there is a role for designers to, enable the product lifespan to be extended?
The problem is not it's global. We didn't disclose the battery. That's true. But battery is in the phone, but battery can be recyclable as well. So the point is that if you can change the battery in a phone, you can. The main pieces of the phone are working very well. So you have just to change the battery, but the battery can be completely recyclable.
So you think that if everything is designed to be chemically recycled, that it doesn't matter how long the lifespan is?
I'm sure that we can design the global systems, and that applies for a phone, but that can apply for other systems, in the scope that they can be recyclable. But that's again, that's a different way of thinking, the different way of behaving, and that's a different way of making the things so that they can go into the global and virtuous circular economy.
And don't you also need a lot of energy to, get all these chemical processes, to be done for each smartphone? Like now, people put them in their drawer at home and they forget about it, or they get through the shredder probably.
Right.
Maybe they take the battery out, but this is a lot more effort.
Yeah.
Are those is that negative that you need more energy?
I think again, it's a matter of behavior of the people and of the people realizing that they have to behave completely differently and to take care about what they have. And before throwing, or as you were mentioning, forgetting in the drawer, to really take care about what we have in terms of materials and to put them in this circle of a global economy, global circular economy. So that will come because collecting is key, and that will come from our behaviors and probably from some global advertising about how to do that. Because the people we don't do it most of the time, we don't do them from if we don't recall them that we need to respect nature. We need to take all this circle into account.
Shall we go to the next product?
Right.
Spin the wheel again. An airbag.
That's good.
Yeah, you have an example for an airbag,
we have
right?
a very good example. We have been developing the project called Move for Earth, which is exactly recycling polyamide from airbags. In a nutshell, an airbag is made from polyamide 6,6 and silicone, and once it's used, you can recycle the polyamide by a chemical treatment, chemical and physical treatment, to separate the silicone from the polyamide, and then by a chemical and mechanical treatment, we can recycle the polyamide to make it back in technical polymers. In this case, we don't recycle, most of the time we don't recycle the polyamide for new airbags, but we recycle to technical polymers that go, for example, in parts for cars, but the polyamide is completely recycled.
So you have two main chemicals in airbags.
Yeah.
And you started to recycle that at the end of the life of the airbag. Why an airbag and why these two materials?
Because, well, these two materials is really based on you need to have these two materials to make the airbag, which is kind of a balloon to make it work, and to make it withstand on the pressure and so on. So this is the technology has needed that. But then we realized that there is a lot of potential for the recycling of airbags that come from the global economy of the recycling of the car. And so there was a huge amount of potential polyamide to recycle. So that's why we started this project more than 10 years ago. And because it's really an interesting feedstock for polyamide.
So you say that with the polyamide, one of the chemicals that you restore after it, you can restore it, but only for other applications, not to bring back to the airbag.
Well, in this case, the global economy was more to go to technical parts, because it was easier to make it, to reuse the polyamide into technical parts. This kind of technical polymers.
Is that downcycling? Is it
Not
an
really,
example of that the quality of the material goes down?
No, the quality is the same. It's still the same PI66, and it's just applied to other, because the way to recycle leads to small pellets, and these pellets are really easy to put in the polymerization of and to make in the extruders, for example, and to make technical parts.
Okay.
So it's a global interest of the system.
So how is that loop closed? Obviously, when you have an accident with your car, you need to go to a garage.
Yeah.
Do they bring that back to the manufacturer? Like how does the system around it work?
Well, there is a complete system that collects the airbags from the car manufacturer, well, the car dismantlers, and so point was to organize this global system that we can collect. I hope you have the least accidents with your cars, of course, but it also comes from used cars, and so there is a global system of collecting.
Okay, shall we go to the next one?
Yeah.
We have a few more to go.
Go.
Okay, let's spin the wheel. Still car related.
Yeah.
Still car related. So I do have an example of a tire that has been reused, because sometimes they grind them up, these tires, the old tires, and they use them in playgrounds for children.
Yeah.
But it's actually quite bad for their health, because there are chemicals in there that are actually not good, especially for small children to have like contact with their skin. What are your reflections on, reusing tires? Like, can you actually recycle them? It's an elastomer, right?
I think that can be done. Again, that's true that tires are ground most of the time for reuse today, or burned sometimes, or they go into some additives in cement manufacturing, if I'm not wrong. But based on the fact that the tire is mainly an elastomer plus fillers, silica that is provided most of the time by Solvay, and carbon, but also some metals inside. So it's a very complex system. But again, if we want to recycle and to go back to the basic molecules that have been used to make the elastomer, to separate the silica, to separate the other components, that I don't see any reason why this shouldn't be done.
Why is it not being done now?
Maybe the key reason is the economics. Again, we need to, I'm not an expert in tires, but I think we would have to think about the global economics if we go, and to find the projects, the processes, of course, because you need to find a process to dissolve the elastomer, then to separate again from the other components. But we could recycle silica, we could recycle carbon, which is carbon black, which is inside. We could recycle the elastomer back to the basic monomers. So I don't see any chemical reason why that wouldn't happen. But of course, we have to think about the economics, and this would be maybe today always one of the limitations. But this is something that we can think about, and it's a very good question.
So what do we need to change around the economics to enable
well,
something
the first
like
is
tires?
yes, the first is to find the process, to realize, to show that recycling the tire globally would be better than, would have a better economics than to put it to recycle the way it is done today. But that's true that you have mentioned, that has to be proven, but you have mentioned that there could be some harmful effect. I don't know, I'm not aware of these kind of effects, but if there are some effects, that we have to take that into account. So one of the key points would be the necessity to find other ways to reuse tires. And the other point would be, of course, if we get the economics, we can think about developing these kind of processes. But it's still the same, always the same point. Are we ready to go into these kind of projects? Are we ready to invest? Because we need to invest. We need to invest in the economics, and in these projects. And how much are we ready to go into these kind of projects, having in mind that the economics will be good maybe within 10 or 20 years from now?
Can you already start changing the chemistry of a tire to make it already suitable for, like in the future, for easier recycling?
I think that has to be asked to the tire manufacturers, because they know, of course, exactly. They have been developing the chemistry and the physical chemistry and the physics of tires in a very specific way, so that the tires work the way they do. Of course, the problem is always if you change the chemistry, you change the physical properties, and that can be detrimental to the usage. So it's really something, but I'm sure that the tire manufacturers would have
it is also a bit of a
relevant
trade-off,
answer.
right?
I'm sorry.
Because it's also a bit of a trade-off, because the chemistry is now the way that it is, because we want efficient fuel use for our cars.
Yeah.
And we want grip on the road,
Yeah.
but not too much, just the right amount for
Right.
safety.
Right.
So it's difficult to also make that chemical transition if you don't want to make any compromises on those qualities.
Always.
Right?
Always there is a, when you modify the chemistry, you modify the physics, and you are doing with materials based from this chemistry, you will modify the physics, you will modify the materials, the properties of the material, and totally agree with you. In the end, you will have to take into account some compromise between what you want to do in terms of sustainable development and what you want to get in terms of property.
Should we go to the next product?
Yes.
Okay. LED lamp.
Oh.
This is part
Good.
of the transition towards more efficient
Completely.
energy use.
Completely.
A lot of people think, if they use an LED, that is something, for suitable for a circular economy.
Right.
Is it?
Well, for circular economy, I don't know. For energy savings, yes, definitely it is today, because the LEDs are developing because they are much less energy consuming than fluorescent lamps, which were already much less energy consuming than the incandescent lamps. The point is today, I'm not sure that the people are taking into account the point of recycling LEDs, because they have a very long lifetime. They're supposed, and I think when you buy an LED, you realize that, they're supposed to last at least 10 years. So I'm not sure that we are yet, and that's a mistake, because we have to anticipate that in the point of recycling of LEDs. But that's the same. LED is mainly polymers, plastics, metals, and the active species, which is gallium nitride with a phosphor, which is a luminescent material, which is the yttrium aluminum garnet, again rare earth is yttrium. This is the key point in the future. There will be a lot, gallium is very scarce, yttrium may be a bit scarce as well. So at some time we'll have to recover the LED from the LEDs. There will be billions, why not to say trillions of LEDs all over the world. After they come to the end of use of the first generation, there probably will be an interest in recycling the LEDs and recovering the gallium, the yttrium, the other metals, and possibly the polymers from the LEDs. So in this case, it's again dismantling, and then the chemistry can play a significant role in the recovery of gallium. All these kind of chemical systems to recover gallium, to purify, are known because they come from the industry of gallium. And so I don't see any limitation to the recycling of LEDs.
Does it happen
The main
nowadays?
point will be collecting, sorry.
Oh, does it happen nowadays that they are being recycled?
I'm not sure. I don't know. I don't know, but they're probably getting collected. I'm not aware of recycling, but this has to be checked. Because in the end, when you see the development of the LEDs and how many LEDs we will have, I think it's a very important topic.
So if I look at an LED,
Yeah.
it's very difficult to mechanically separate these different bits, right?
I'm not sure.
You have the metals are part of the plastics, like they're melted in there. Do you think that you need to sacrifice some of the materials to restore the materials like gallium that are much more rare, and that you have to prioritize some materials over others?
Maybe, that's a very good question. I think we would have to check, again, globally on the economics. It is true that in LED, as you know, they are very small pieces, so there is a very small part of gallium, but when you multiply by thousands of LEDs, that comes to significant. So we would have to make the economics on what is the key importance, what is the importance of gallium, what is the importance of yttrium with respect to other metals or to polymers, and then to see whether we need to sacrifice something. In the end, it will not be sacrificed, because it's just when you dismantle, at some time you will get some polymers, you will get some non-precious metals, you will get the precious metals, and then it's a matter of what you do with them. But because you will need to sort them, and you will need to get at least the concentrate where you get the gallium and the yttrium. So maybe we will not have to sacrifice. We have to prioritize, probably, but not to sacrifice.
Okay, next product.
No.
Energy
Solar.
related again, solar panels. Massive transition towards, generating electricity through renewable energy sources. And you see a massive investment in solar panels, especially from consumers themselves that have solar panels on their roof.
Yes.
Do you think that this is a good transition towards solar panels? Is this going to work in the long term? Are we able to restore them again after the use?
It's the same. I think I'm not sure that today we are really looking at the recycling of solar panels, because also they're supposed to last for at least 10 years. We will see on the long term. Again, solar panel is made of silicon, which is the active species. They're made of polymers. It's made of resins to make the joints, the links. It's made of metals to make the electrodes. So it's the same. We can possibly dismantle the solar panels and get all the species separated. Now the point will be, can we reactivate silicon, which I don't believe, so we probably have to go through some process, but we can imagine to get back the silicon and to put him back to the silicon industry. And the other parts, again, metals can be recycled, polymers can probably be probably be recycled. So it's a bit the same, but in a larger scale. That's what we have for LEDs, because we have also some precious metals in solar panels. So the point would be to collect, to dismantle, and then to find the chemical processes that would be economical, and to go into recycling. But as you mentioned, given the huge amount of solar panels, the problem will probably arise in the next 10 years when they come to the end of life.
And when they come to the end of life and we have the solution, we can recycle them in a couple of years from now.
Yeah.
They probably do require some energy to recycle. But
That's true.
And they're there to actually generate energy.
Yeah.
Do you think that maybe that trade-off is also going to happen in, energy invested versus, the return on energy in a lifespan? Do you think it's going to work with solar panels?
Again, maybe if you are using energy that will be coming from the other solar panels, you will come into a
But then you create solar panels to recycle solar panels.
True. No, but that's true. That's why we need to make the economics, and we need to meet the global economical evaluation of the projects, because that's true that sometimes the energy that you will need may be too high to make the process completely economically viable. But on the other hand, you need to do something with these panels. So at some times, again, it will be a compromise between the cost that we will need to recycle and the necessity we will have not to have these solar panels everywhere or just in a discharge place.
We just had a very interesting question that came in from Pauline, and she talks about that there have been diff sessions that are really clearly talking about how we learn from nature to make a system work, and especially when you look at nutrients, right? If we look at one of these showcases that we just had, how can we learn from nature to close the loop?
A lot. In chemistry learns a lot from nature, and will learn a lot. The problem is not to completely mimic the nature, but is to get inspired. And for example, photosynthesis is something that is inspiring chemistry in terms of how to reproduce it. But the problem for photosynthesis is very slow, so we need to try to find chemical processes that can be accelerated by some energy. At the time, there is no free lunch, but we are really looking at these kind of things. We are looking at some of the specificities that nature gives to plants, to animals, to understand how it works. For example, the so-called lotus leaf, the superhydrophobicity, that you get on some leaves, and we try to reproduce that by either bio-based chemicals or traditional chemicals and physics, because in the end you realize that not only it's the chemical composition but also the nature of the surface that brings the property. So we can work on surface modification, we can work on mechanical properties. You need that some shells have very, very strong mechanical properties, so we try to understand what is the structure to be able to reproduce these kind of things by the chemistry. So we are more and more going into what's so-called bio-inspired materials. Again, the idea is really not to mimic and to do exactly the same, because nature has, again, longer time scale, but is really to understand, to analyze exactly what nature has been doing and to reproduce by chemical processes. So definitely, yes, the chemistry is getting more and more. The chemistry and the physics need to be more and more inspired by nature. But again, understanding what's ongoing, not only just trying to do it.
But nature doesn't have IP. Nature is open source, right?
Yes.
All the leaves that fall off a tree go to the soil again. I know that you have 60 patents. Congratulations, by the way. But it's IP, intellectual property, patents, kind of keeping the information disclosed.
Yes.
Do you think that needs to change if we want to transition towards something that is a bit more intelligent and learns from nature?
Well, that's a kind of a philosophical question.
Is it?
No, industry is based on IP because we protect our markets, we protect our businesses through IP. And so I don't see, at least in the medium term, a big change on that. As long as we have industrial companies, we need to protect. The point is, what I would talk about IP or the way we work, is we work on a more and more open and collaborative way. We work with academia, and we need to get knowledge from academia. We work with customers. We need to get the challenges of our customers to anticipate and to make them to bring them value through the solutions we bring with our products. And we need to work with sometimes partners, with startups, even our competitors. Sometimes we are joint projects. So the model is more global, and we need to understand also the needs of the citizens, of yourself and myself, when we are as citizens. So the model is coming more and more open, more and more collaborative, and we are more working with agreements and shared IP or shared value, as long as we create more. So today, I don't see a real move on that, and on the contrary, we need to reinforce our IP, our protection, or what we get, but we probably need to do it in a more open way through these kind of collaborations, and particularly, of course, with our customers.
Shall we go to the last example of today?
Right, let's go.
Great, let's spin the wheel.
What's the surprise?
Okay, last one, a car. Are we going to have cars in a circular economy?
I think that, I don't have the real number, but I think that 80% of the car or more is already recycled. So really, the car is part of the circular. It has been probably one of the first examples of circular economy. Of course, there is a lot of metal, and the metal is recycled, but several other parts are recycled. We are speaking about polymers. We can improve the value from the recycling of the polymers. So I was mentioning the case of airbags. So we can improve the recycling even more, and the value that we can in recycling the car. But definitely, it's something that is completely part of the of the circular economy.
I've heard that there were massive supply restrictions, or there was not enough supply of lithium for, especially if you have these electric vehicles.
Yeah.
Do you think companies like yourself can keep up with the demand if we all move towards electric vehicles?
Well, first, today there is no lack of supply because there are not enough electric vehicles yet to use a lot of batteries. So the problem is not for today. It may arise in the longer term if there is a huge development of lithium-based batteries. But still, the supply is here, and there are several ways. One way would be and that people are working on that, to use batteries that would not use lithium but sodium, for example. This is a very long-term project, but that may happen. The other way is to get more lithium from the mines, and some people are working on getting lithium from the sea. So that may be also a long-term but interesting projects to work. And the other part, of course, will be recycling. Battery is a very complex system. You have the lithium electrolyte, you have the electrodes, you have cobalt, you have manganese in the cathode, so that can be replaced by iron. You have carbon, you have sometimes lithium metal in the anodes, and of silicon. And all this is chemistry. And again, I'm sure that, and people are starting to work on that, we can dismantle a battery, or lithium battery, and recover lithium, cobalt, manganese, or all the components of the battery through chemical or hydrometallurgy. And so I believe that there is, whatever the development of the batteries is, it will have to go with also a development of the recycling system of the batteries.
So we have a question that came in from Alex, and he said, I understood that some materials are great for recycling, aluminium for example, and others are not so good. But you are talking as if everything could be recycled at a high quality. Can it?
I'm sure that chemistry can do it. This is my conviction. I don't know, sorry. This is my conviction that chemistry can do it. Now we have to treat case by case. We have to evaluate for each time what is the technological capability of chemistry to do it and what are the economics. But basically, when you are dealing with chemistry, the chemistry is so huge in terms of science and of technology that you can get from chemistry, whether we talk about the organic chemistry, polymer, inorganic. Chemistry offers almost an infinite variety of technologies that you will be able to use and to adapt to any kind of metal. So definitely I'm convinced that it can work. Again, it's a matter of, do we want to do it? Are we all, the humanity, committed to do it? And do we want to accept sometimes the compromise? But in terms of going to a high purity of metals, chemistry can do it.
Thank you so much.
You're welcome.
We will be hearing from my colleague Molly Marshall what is coming up next during the diff now.
Hi, I'm Molly and I'm really looking forward to 5 p.m. GMT today, where two of the Ellen MacArthur Foundation's Make Fashion Circular team will be talking to us about how we might design a fashion system fit for the 21st century. Another session is one that happened earlier on at the diff, when we were joined by renowned architect Michael Paulin to explore how new digital tools, coupled with vastly superior processing power, have opened up a world of possibilities in architectural design. My last top pick is taking place tomorrow at 5 p.m. GMT, where we'll be joined by Bill McDonough, a globally recognised leader in sustainable design, who will be live in the studio talking to us about cradle-to-cradle principles that can productively transform design decisions at all scales. That's tomorrow at 5 p.m.
And that was all from us here at the live studio of the Disruptive Innovation Festival. Check out the schedule on thinkdiff.co to see all the great sessions coming up today and the rest of the week. You can also catch up on many sessions that already happened in the last 2 weeks. So see you at the next session. Bye.